So thank you very much for having me. As Cecile said already, I'm Igor Obreht. I'm currently working at Maru, and I am dedicated to, now I can say already applications, so not anymore, also development of mass spectrometry imaging on sediments, and which is a relatively novel tool in paleoclimate reconstruction. And I have to mention basically Lars and Kai, who could be considered as godfathers of this technique. And while they also apply this technique in general in the sediment, understanding the biomarker distribution, my kind of focus is really to apply it for the paleoclimate reconstruction. And of course, this is a presentation of me, but presenting really the results of biomolecular team from Maru, and what is the part of organic geochemistry, so Hindring's lab. And I will present you this new technique, but the goal of this technique is really to increase the resolution, how we can study biomarkers from sediments. And as a start, I like this paper that says past climates inform our future, and I think most of us use this term like that the past is the key for understanding and predicting the future, right? But what does it really mean? And what this paper highlights is that we should invest more efforts to actually have the models that can test, the past. And the better they do that, the more likely they will better project the climate and in the future. And the problem that we face there, that the resolution for the projections and current climate trends is much higher. So in subannual to annual level, where our quantitative proxy data is, especially from the sediments, is much often coarser. And VARs are, of course, very important archive, because they do have this potential, as you will know, to preserve this high resolution signal. However, getting really quantitative data such as temperatures, first temperature, is a bit challenging. And one way is using the organic geochemistry that is really limited to centimeter-sized samples. So especially if you have the variability, your lipid biomarkers cannot really unlock this signal that is locked in the sediment. And not only that, we don't have access to variability, which you might have with some other physical properties, but to have been more quantitative, we also don't have information of the amplitude. So one approach to address this is applying mass spectrometry imaging. And this is the technique that was developed in my current working group, and so far application of this technique, so MSI, on the sediment is happening only in our working group. So this is the technique that was developed for the life science, but we have successfully applied it on the sediments. So just to briefly guide you through the workflow, we would sample the cores with LL channels, which are basically a smaller version of U channels, and then divide it into the 5 centimeter samples, and we will embed them into the gelatin and CMC mixture to stabilize them. So we need an undisturbed sediment surface that we would freeze and cut with a cryomicrotome. And the reason we would cut it that way is that for each individual proxy, we would usually use following slide, because we use the destructive technique, and that in order to increase the precision, we would focus mostly close to one biomarker. So when we have our slides, we would apply the MALDI source in the resolution of 100 to 200 micrometers, depending on the sedimentary settings. So basically, we would shoot by laser our section and ionize the molecules that we will detect with a high-resolution mass spectrometer, so FTICRMS. And in each shot, we will have 100 to 1,000 of compounds per each spot, but we will focus only on these targeted biomarkers that will have the specific mass. And we will be very precise in this case. And essentially, this looks something like that we have a sedimentary surface. This is Santa Barbara sediment, and the upper 5 centimeters. And essentially, we would systematically shoot it with a laser around the surface, and you will get something like this. So the imaging, where each spot that you see here is individual measurement. And this would be UK37, so it will be alkinome unsaturation index, which will give us an idea of the temperature. And you can see that instead of this conventional several measurements, we will have this 5 centimeters up to 250 data points if we would average our 200 micrometer resolution. So there is a bit more information about the process, how we do it and treat the samples in Aufken et al. And really what is really cool about it is that we can also use multi-proxy approach. So in this case, each of these samples was done on the following sample. So it was not made on exactly the same sediment surface, but just basically following with another cut, the kind of microtome. And you could see that we could also adjust a bit the surface in order to get more parallel or more perpendicular signal, and that we can have a multi-proxy approach. However, there are also some limitations that I think it's important to note. So, for example, we need to have enough of the organics, so enough of the signal. Our threshold is probably much lower than, actually not probably, it's much lower than with conventional analysis. Another important thing is that we are getting exact masses. So isomers, for example, we cannot distinguish between them. So CCAT is actually GDGT based, so simplified text index, where we couldn't distinguish between CRAN and CRAN prim, right? So we had to go sometimes for more alternative proxy. And also sometimes we have basically the compounds with the same molecular formula, we cannot distinguish with them. So we would have to do some GC analysis or LC analysis to see if one is predominant, so that we can consider that signal mostly comes to that. And when we have the mixture, we just simply cannot distinguish between them. And then we can make the unquote profiles. Another problem that we face is that, for example, ionization of some molecules, especially that are saturated, is not possible. So, for example, we don't have access to N-alkanes. We can use, for example, fatty acids instead, but they're a bit challenging proxy. I will speak about them a bit later. And another approach in multi-proxy kind of analysis is to combine this approach with other imaging techniques such as micro-XRF and for example, hyperspectral imaging. I think we are trying to make some progress there, and this is kind of exciting development happening there, but I will leave that aside for this talk, but I would just like to highlight that this is a great potential there. Another approach that is very promising is using untargeted approach. So basically all those data points that we mentioned that we have, but we don't use, we can try to find some clusters and some systematic, structuring among them and get some hidden information from that. And I'm really not an expert of that. We have Wei Min, who is really very good in this, and he just scratched the surface with the sediments from Santa Barbara. I invite you to look at this paper if you're more interested. But I would really like to focus here rather on those targeted approaches to basically try to address three things. One is, in comparison with instrumental data, how can we understand the molecular proxy signal? Then apply this for the paleoclimate reconstruction. And in this, we would look to the seasonal to multi-decadal variability from the abrupt climate transitions. Somehow, abrupt climate transitions were the most kind of interesting target for the first analysis that we did with this approach. And then I will give a bit of an outlook how much we can use that for continuous records. So when we speak about the understanding of the formation, maybe I should also highlight here, because I have map only here, we will focus on the understanding the formation of the molecular proxy signal in Santa Barbara. We also did, actually Tiffany did in the Arabian Sea, so in green here. The signal from our climate transition will be from Cariaco and Mayfield Amar. And then we would look on the Mediterranean subpropel from last interglacial and Holocene from Arabian Sea. So just to know where we are spatially when I continue talking. So when we go to Santa Barbara, I think there is a record that spans with the mass spectrometry imaging last 100 years, but I will focus only to the interval where we have precise instrumental data. And so you can have here comparison between instrumental data, UK37 and CCAT, which is the simplified TEX86, and also as a RIN index here. And what you can see in comparison to UK37 is that this interannual variability is very well represented, but somehow that this actually the amplitude, maximal amplitude, and some of those seasonal variability are not so well expressed. So the cool thing is that we can also compare that with the other properties for the water column. So in this case, if you would calculate the difference here, so look on the residual temperature between the reconstruction and the real data, you would see that this difference is really controlled by the nitrate concentration water column. So we can really now better understand, here is also the example how it's like driven, that what drives our and what influence our signal. And the cool thing is that this is also confirming the cultural studies, or it's confirmed by cultural studies. When it comes to the CCAT, things get a bit more complicated, but because it doesn't really seem to record very precisely what is happening at the surface. And when you look at with the other properties for the water column, you see that there is a link with the upwelling intensity. And in particular, when you compare it with the Pacific decadal oscillations, or El Nino index, or North Pacific gyro oscillation, you start to see some similarities that are potentially really driving this signal. So we can conclude that what drives our signal is mostly temperature, especially with alkanones, while this seasonal variability can be affected with the nutrients, but the upwelling is really in this upwelling regions, so not in the open ocean where those GGGD proxy could be probably more representative of the temperature, but it's hard to get really this undisturbed varved signal sediments. In this upwelling intensities, that they are mostly represent these changes in the upwelling. And the similar results are really from the Arabian Sea, which I will, due to time constraints, not present here, but I invite you to look at the paper. The only difference is that this subannual variability was a bit muted in Arabian Sea, and then after the damming of the Nile River and surrounding rivers, there was shift in the regime. And from here, I think you are convinced to the certain level that our at least alkanone-based reconstruction is very reliable for reconstruction this annual to interannual variability. And therefore, I would like to take you to the Cariaco Basin, where there is a last 15,000 years of well, strictly speaking, I don't know if all of them are varves, but the couplets of light and dark layers. So mostly I believe that there is a strong argument that most of them are annual. And we will look on the younger dryas holes in transition. So Lars actually provided this graph that will show that when we go from the younger dryas to Holocene, that sediment gets much darker, and this is because we have more rain. So ITCZ is coming more to the north, and during winter we have upwelling, which will make those lighter couplets. And at the same time, so we have more precipitation, and this can be confirmed with the decrease in the fatty acids chain lengths, which means we have shift from C4 to C3 vegetation. So also indication of more precipitation. However, when we look on the sea surface temperature, we get completely confusing signals. So alkenones don't show any change. Foraminifera shows warming, and GDGT shows cooling. So very confusing. So what the record that was provided here was really in the 100 micrometer resolution. So it can be few data points within each couplet of varves. And what Lars basically showed here is that there was not much change during this transition. There was this short-lived interval and perhaps warming afterwards, but this transition was very kind of not prominent. What you can see from here is that the subdecadal, so probably El Nino really started to be more intensive, and also about a bit more on the decadal variability, multi-decadal variability intensified. But you cannot see very much from this here. The cool thing is if you rely on this correlative approach, that when you have cooling in Greenland, it would be related to the warming in the tropics, which means that probably is related to AMOC and the sea surface temperature will be warmer when you have the cooling in the northern hemisphere. But this does not really give you indication of the big change. However, if you look at the seasonality, and this is possible by using the imaging approach, where you can, on the same sediment surface, look at the sediment color, and here was also supplemented with the micro XRF elemental mapping. You can see that when you have darker layers, you have more titanium and iron, which come from the terrestrial, so more rain. When you have a lighter, you have more silica, so coming from the diatoms, this upwelling season. And you can see same from the temperature. When it's upwelling, it's colder, it's this winter. And when it's warmer, in these darker layers, you see higher temperatures. So you can compare that over the record. And what you can see is actually that the absolute temperature doesn't change, the seasonality. So summer became much warmer with the onset of the Holocene. And this is something that is not really possible to reconstruct by using the conventional method. And this is, I think, really brilliant example of what we can do with this imaging when we have enough of resolution. And perhaps that can also explain why the forums are showing increase if they're having preference for warmer summer temperature or not upwelling seasons. Okay. Somehow a bit mechanistic for this is still missing. Why is that happening? And this is really that we are just opening this part as a new field, that we don't actually have the models that try to simulate that, and we also don't have other tropics suitable sediments to actually compare that. But I think there is a great potential in actually testing this further. And in this case, I will go to the only lake sediment that I will present today. And this here will look on the transition from the Allerod to Younger Dryas in Western Europe. And we will go to the Lake Mefeld-Amar, one of the, probably among the best varve records, I would say, in Europe, or at least in Germany. And it is also one of the most extensively studied varve lakes in this transition. So there is a paper from almost more than 15 years ago that shows that transition this from Allerod to Younger Dryas happened very suddenly in almost 1 year. But there was another paper coming, which now became a bit controversial, and I will come to that, where it is based on a paper before that on Lane et al. From 2013, where they detected the VDH in Mefeld-Amar, which is present also in Greenland. So they could count the layers until the transition, and they detected that there is 180 years difference between onset of Greenland stadial 1 and Younger Dryas in Western Europe. Right. So we went there in order to actually understand how did the vegetation respond to the Younger Dryas, which happened somewhere here. Onset of Younger Dryas is here. I should have probably indicated that. This is Lacha Tefa. But also we wanted to see if we can explain this time progressive onset of younger dryas in the Western Europe. So what we see used here is fatty acids actually, and they are, not as an alkane specific only to the higher vegetation. They are mostly specific to the higher vegetation. So we also had a lot of wet chemistry analysis to show that they are coming mostly from the terrestrial sources. So we use average chain length, and we use terrestrial to aquatic ratio. So here we used short chain fatty acids um, in comparison to long chain fatty acids. So essentially the average chain length would be higher when you have higher temperatures or more humidity, and vice versa. And the terrestrial to aquatic ratio would indicate with a higher values probably more terrestrial runoff input. So very, skeptically, if you look, you could say it present precipitation, but that should really take my care. But what is really interesting here is that we get this variability that is also resolved with a very high resolution pollen accumulation rates. And this is really cool because unlike usual pollen analysis, pollen accumulation rates react instantly. So when you have warming or more precipitation, you don't have to wait for vegetation to change, but the amount of pollen reacts at the same level like the average chain length of the leaves. And this was used to actually look at what was response of the vegetation to the younger dry, so we could see that there is cooling. But back then we really were excited to compare that with Greenland. And as I said, there is this time transgressive lag where this is a Greenland temperature. So the Ethereum excess, it's usually plotted the other way around. I just put because of this correlation that I will show. So this is onset of, it is used for distinguish onset of the Greenland stadial 1. And you could see when you have higher values, you have more distant source of the precipitation. So they're coming from other sources coming from mid or low latitudes. And you could see that there is a link there that we also calculated statistically with this age model that was mostly for this interval valid. And another interesting thing is really that when we have the cooling here or indication in the cooling and decrease in precipitation, it fits very nicely to this Greenland interstadial 1b, which is a cooling in this warmer stage. And even if you look in a bit more details, you see that this correlation is there only until this N-grip potassium sodium increase, which is indication of the significant growth of the sea ice around Greenland. So our interpretation was like that during the Allerud you had those westerlies that were following probably similar track as today, but when you had this time progressive lag with the cooling of the northern hemisphere, we would have a shift of the ice from the east that will develop, sea ice would develop much faster because of the narrow range and between the Greenland and lower Antian ice sheet. And the westerlies would be shifted to the south, bringing this distant source of moisture to Greenland, but also bringing warmer air to the Europe. And then with the increase in the sea ice around, with this sodium in Greenland, we would consider that it was like westerlies would go to this zonal mode, and that was this abrupt shift and younger dryas. And to test that, we actually looked on the southwestern Iberian shelf, and this is all same core, which will show the same, right? Because we hypothesized if we see it here in Central Europe, we also have to see it with this hypothesis also in the Iberian margin. And this fit very nicely until the paper was published that shows that our age model is probably very wrong, for 120 years wrong. And then Lacher ZF is not where we have it here, but that it will be moved a bit to the past. And you can do that. Well, there was a paper that proposed where you could correlate the tephra. And if you do that, this would be Lacher tephra from Methyldamar would be correlated to this peak here. you can probably study this from another perspective. I also would kind of refrain from doing much from here because the true problem is what happened actually with the varves. But I would also like to indicate that having a high resolution approach is very important because even in these settings, we see that there is a very interesting phase of this time progressive behavior until we get the onset of younger dryas, and that actually those we are now out of phase with Greenland in the Allerode. So when you have cooling in Greenland, you would have warming and more precipitation in Central Europe, also to the late Allerode, right? So speaking about this climate system being synchronous, I would like to indicate that we should take care of that. And really, I think imaging techniques, can help here to understand what happened and if those varves really are missing. But this is something for a bit of the future. I mean, as someone who worked on Marine Institute, I had a bit of a struggle really having that as a main focus. But I'm very kind of fascinated by this to actually see what happened here. Nonetheless, I don't want to leave you on this kind of cliffhanger note, but I will go to take you to the Mediterranean to present you something that I like to call first continuous annually resolved record of Earth's climate from warmer than present world that is kind of continuous in the sense of multi-centennial length. And we will be here east of Crete, where we have a very cool subpropel that is the first 9 centimeters, this is around 90 centimeters, first 9 centimeters are not annually laminated. Then we have those annual laminations that are based on sinking of the diatom mats. So the first indication of the breakdown of the water column and probably establishing of oceanographic conditions more similar to today than what was, during the year-long stratification. And this is another example of the imaging, how we would do it. This is 5 centimeter sample. And what we got here is really, I think, very cool time series. Here in black is 50, running mean of 50 data points. So our resolution is really in this annually resolved part to annual, right? We use 200 micrometer resolution, and I think average varve thickness is around 240 micrometers. And the idea was actually we have now the opportunity for the first time to compare that with current and projected trends. So last warmer than present world, and in particular this varve part showed that there are no actually decades. So what we use here also 30 years intervals. So difference of the 30 years intervals in 10 years. So in the decades, also to account that those varves are maybe not necessarily strictive varves, that they were not very regular. I mean, that it was possible that few of them are missing. So we used a bit more kind of well, skeptical approach, but we still provide very good data. So we saw that that the decades that were in the last interglacial were not warmer than what we observe today, at least not in this annually resolved part. And what is even more important, even if they are on the similar range, they were not consecutive decades. And this is something that we already in the next few decades, we will outpace anything similar that we saw in the last interglacial. And while this is not surprising, this is actually the first proxy evidence to show that. So this was kind of the significance. And you might wonder about this part here that is not laminated. This part is also heavily affected with oceanographic conditions that were significantly different than today. And actually to demonstrate that, I will not spend much time on that, but I thought it's cool to show you. We also use this multi-proxy approach and reconstructed another time series that is based on GDGTs, and it looked completely different. It's almost to the level that it's crazy. But we also expected it to look different because we know that the GDGTs do not record very precisely temperature during subpropels, but are affected with other factors, probably mostly ammonia oxidation rate. But what we wanted to test is really if this is related to the temperature, we can see any relationship between those two proxies. And actually we can. In the multi-decadal range, you could see we defined here different oceanographic conditions, and they're really changing following those changes. So those changes are established completely dependently of the temperatures. And we could really see that there is a strong link, but mostly in the antiphase. And even if you look here in the multi-centennial range, we would see that particularly in this early stage that is not far, those two temperature, the proxy cancel each other, which means that this reorganization of the water column was really main driver of the temperature change and not the exchange of the heat as in the later stage of the subprotel. So again, confirming that hypothesis that we had in the first paper. So we kind of now provide also an evidence that this was really the truth, that this first part of the subprotel was not representative of the today's conditions. And then, so a bit counterintuitively, I'm not going deeper in past and coming back to Holocene, but the reason I left it for the end is because I'm not talking now about the Varves sediments. I'm talking about the finely laminated sediments from the Arabian Sea. But the idea to really do that and not focus on Varves was really to test if we can provide continuous records from almost entire Holocene that are representative. So, I mean, instead of going in the 10 meters from Cariaco or something, we decided to go to the Arabian Sea, where we could look everything into 2 meters and then kind of compare it. So this was a bit of a trade-off, and that's why I leave it for the end. But it's very interesting section because it is a not upwelling part of the Arabian Sea, which means that the sedimentary dynamic is controlled by precipitation, so summer monsoon, but the sea surface temperature is controlled by the Indian winter monsoon. So it also gives you a possibility to understand this interaction between summer and winter monsoon, which is extremely rare setting. So this is the sediment, and the idea was really to focus on the Holocene, because this is all very finely laminated. We have first bioturbations, or major bioturbation with the onset of younger dryas. However, the last 2,000 years were not successful because as we confirm with the conventional data, that the detection limit was what the concentration of the alkanols was below our detection limit. So this is how the sea surface temperature reconstruction looks like. And of course, without the age model, this is all kind of worthless. So our age model is not based on the annual layers counting, but we have, I think, pretty robust age model with 22 radiocarbon samples on about 2 meters of sediment. And, you know, for the most of the record, our resolution is 1 year or below, only those intervals with high resolution of, so 200 micrometers present mostly 1 year or below, but we cannot speak about this variability because of the age model uncertainty. So I will focus only very briefly on the multi-decadal variability, but I would rather like to provide you actually the idea how reliably this approach is in these long records. So I will present you here also very time-consuming analysis of almost 100 samples with conventional analysis that actually fit very nicely to our sea surface temperature reconstruction. So I think that I can convince you with this at least that we are doing actually quite a good job. Although, you know, we are using calibration for the GC, we are providing very precise data sets. And this allows us to actually compare our data with the sedimentary settings such as color, you know, simply in the resolution that was not possible before. And I would just like to highlight that our ongoing work is really trying to, this is the same sediment, right? To link this to with beryllium-10 to the solar cycle. So essentially that we can correlate our records directly with the ice cores. And so this is the 14C production rate, so basically solar activities. And this is our sea surface temperature reconstruction, sedimentary dynamic based on reflectance. And those are just, as a Northern Hemisphere record, I took here this mare because it is a newly published paper on the multi-decadal variability or decadal from the Western Europe. Then we have the Cariaco as indicator of tropics. And basically everything that has the resolution that can compare shows that multi-decadal variability increased somewhere here around 4,000, as you can see here, uh, probably due to intensification of the enzo. Even our sedimentary dynamics shows higher variability, probably due to the summer monsoon, but only our record shows decrease in variability. And the only other record that I could find is actually the record that we are trying to tune it to. So we still don't have the data, but it is perhaps possible that this, winter monsoon was a bit controlled with the variability of the solar cycle. That's, very much working hypothesis, but we will test that. But what I want to really highlight here is that even if we don't have those varved sediments, we can provide a very robust data and very interesting data. And just if you imagine if we would do that on the varved sediment with a very high precision, we would probably have an excellent record. And this is probably one of the next steps. Okay, with this, I would really like to just wrap it up and really kind of hope that I could convince you that mass spectrometry imaging is a very powerful tool, and not only for understanding of the proxy signal in comparison to the instrumental data, but really for the paleoclimate reconstruction. And I think there is a large potential to go a bit more into this multi-proxy approach, in particular, kind of going more to the lake sediments and trying to find the good proxies, which we are still struggling a bit with. And also that really includes this combination with other imaging techniques that are probably faster, but slightly less quantitative. And of course, there is this potential of untargeted approach. And with this, I would like to, acknowledge that this project was actually, the whole method was developed under Zumeckler project based on ERC, and we are now currently working on the DFG funding. And of course, I would like to thank to my group members. It's probably one of the best group that I could imagine that someone can work. And I also want to thank you for your attention and for inviting me here.